Okay, here's another common reaction. It's an addition reaction of an alkene where we're going to add Br and OH. It's halohydrin formation. So it's the exact same mechanism as the addition of Br2, but now that we're going to add the presence of water, the water is going to be the second thing that attacks instead of another bromide. Now, the reasoning behind the stereoselective outcome is the same as in the addition of Br2. That's going to be a reason that's going to pop up several times throughout the course of this chapter. So we want to make sure that we're paying attention to that. So what's going to happen first is that, and I'm going to just rewrite Br2 so that we can see it and all of its lone pair glory. We're going to have a lone pair attack the bromine from the pi bond, and it's not a lone pair, but it's the pi bond, at the same time that a lone pair from bromine is attacking back into the pi bond from the alkene. Okay, so what is the result of that? It is an intermediate, and now I'm going to use a good old, I think these are Haworth projections, if I remember my vocabulary correctly, a Haworth projection to sort of show the three-dimensional aspects of this particular intermediate. So I've got my six-membered ring here. And so what do we have? I've got a CH3 group. It could be pointing down, could be pointing up, but I also then formed a cyclic intermediate. And this is a bromonium ion. And the reason that the subsequent addition happens in the opposite direction of the bromine in the final product is that this bromonium ion prevents additional attacks, and in this case it's going to be water, from the same side that the ring, this three-membered ring that is this bromonium ion, has formed itself. So the only option that I have for water is for water to attack from below. And so that's what it's going to do. Now, this also has a regioselective outcome in addition to the stereochemical outcome. From a regioselective standpoint, the water is going to add to the more substituted side of the double bond. And the reason that is because in the intermediate of the bromonium ion, it's going to have some, we can kind of look at it like resonance, but really we want to look at it sort of and combine it more with hyperconjugation and this idea that, well, one part of this ring could be a little bit more positive than the other part. And so at some point, what's going to happen is one of these bonds is going to have to break so that the bromine can kind of be singly bound to the ring. And so that means that one of the locations that it's attached to, either here or here, will have to start to gain some positive characteristics. And when we say, okay, well, which side is more likely to start to gain positive characteristic, we say, okay, it's going to be the more substituted location. So the more substituted location will become a little bit more stable when those that partial positive charge starts to form. And so that's why the OH is going to attack that position more readily. So there's two things that are going on, the stereochemistry, and that's that the OH and the H will be, the OH and the Br will be pointing in opposite directions, and that the OH is going to add to the more substituted side. But in order to make it an OH, we have to think about the result. And now I'm going to go ahead and just go back to regular projection. So I've got a CH3 pointing, let's make that, we're going to have to make that point up. To be consistent with the previous picture, I've got the OH, the water now pointing down, and let's go ahead and show out the bonds. And I've got the bromine pointing up. Now, certainly this could have happened the other direction, right? So the CH could have been forced in the other direction. You know, in other words, where the ethyl group is pointing in the same direction as the bromonium ion in the intermediate, which would lead to the opposite stereo configuration of the chiral centers. Now, we could get into a deeper conversation about that not being as likely because of the steric hindrance, but that's a little bit deeper of a conversation to have. But at this point, what we need to do is we need to have something come along, and bromide is fine to deprotonate this water, and then at the end of the day, the product that you form is the OH having added to the more substituted side, and the bromine pointing the opposite direction as the OH. And you could also say that you have the opposite stereo configuration as well. Again, there might be some reasons why that's not as favored as the other one, but it certainly is possible. Okay.